Thank you everyone for coming to Theory Lunch. Today we have Zoe from MIT. She will talk to us about AI safety via interactive proofs. Thank you, Zoe, for coming.
Okay, so hi, I'm Zoe, and today I'll be presenting how to avoid debate, scalable AI safety via doubly-efficient interactive proofs. And this is joint work with Dan Chen and Yong Fan. So I'll start by talking about the AI safety problem that we were trying to address, which is called scalable oversight. So this problem is concerned with overseeing AI systems even as their abilities scale. So this is the question, and the concern is that as these AI models, as we're training these AI models to perform these more and more complex and time-consuming tasks, we might no longer be able to assess that they're performing these tasks correctly. Because even if we do know how to perform tasks ourselves, just because it's so time-consuming, we won't be able to efficiently assess whether an AI is doing it to our liking. So we could consider like a concrete example. Let's think about the scenario where we're training an AI to write some sort of long, high-stakes document, like a legal document, for instance. So during training, the AI is going to output some sort of candidate document, and we'll need to assess it. We'll need to say whether the document is good or bad. And one way of doing this, one straightforward way, would be to have some sort of expert just carefully read over this entire document and verify that it's correct. Where correctness here depends on the expert's judgment, it depends on human judgment. But this procedure seems like it would be really time-consuming, and in particular, it's probably too time-consuming in order to just give feedback on one document. So in a scenario like this, we would really want to have some sort of more efficient protocol for verifying that an AI is doing this task correctly. So this was the focus of this work, was designing efficient protocols for assessing an AI model during training. So this brings us to part 2, which is interactive proofs and cryptography. So an interactive proof is this protocol between a powerful prover and a weak verifier, where the prover tries to convince the verifier of some statement. And at a high level, it seems like it really applies to this scalable oversight problem. So in more detail, we have that it's an interactive protocol between a powerful prover P and a weak probabilistic verifier V. P is going to try to convince V that some statement is correct. And for security, the protocol should satisfy these 2 guarantees. So the first is completeness. If the statement is indeed correct, then the verifier should accept with probability say at least 2/3. And for soundness, if the statement is incorrect, then the verifier shouldn't be convinced with probability say at least 2/3. So this definition is due concurrently to Doubly in 1985 and Bulldozer in 1985. And I'll also note a couple things here. So in this work, we're also interested in not just interactive proofs, not just in proof systems, but also in argument systems. So an argument system is defined just the same, except that this soundness condition is only required to hold against efficient provers. In the interactive proof definition, soundness is stronger, it has to hold against all provers, even the computationally unbounded ones. And also, the focus of this work is going to be on interactive proof in argument systems, or proving that the output of some computation is correct. So the statements that we're going to be interested in are of the form algorithm A outputs 1 input X. So the rest of this talk is going to be on how to apply these interactive proofs to this scalable oversight problem. So it seems like they really just do apply directly. Like if we went back to this document example, it seems like what we would want to do is just take the prover to be an AI and the verifier to be a human. And now what we want is for the AI to convince the human that the document that they outputted is correct. And and the human should be efficient, and also, if the document is incorrect, they shouldn't be convinced. So it seems like we have everything we want, and we're just kind of done. But there is an issue, and it turns out that these standard interactive proofs don't really seem to apply so nicely to this scalable oversight AI safety setting because of this issue of how we define correctness. So correctness in this setting, it seems like we want some sort of fuzzier notion of correctness that's maybe not like the mathematically well-defined notion that we have in the standard interactive proof setting. So we're going to see that we want to maybe consider then a different model of interactive proofs for this scalable oversight setting. So in this setting, correctness might depend on human judgment. Like just going back to this running example, there with the documents, like correctness depended on the judgment of that human expert, right? And this is a human judgment is maybe some sort of fuzzy notion. So the question is then, how can we model human judgment? So we have like a few choices. So we could model human judgment, maybe as like a Turing machine or a Boolean circuit, one of these standard models of computation is maybe the first choice. But this doesn't seem to make so much sense. What seems more appropriate is to model human judgment as some sort of black box function, or as an oracle. So black box function, right, it just takes as input and input, and it gives us the output, and we don't know what happens in between, we can't see the inner workings, and this seems like really appropriate for modeling human judgment. So then, then that's going to be the goal of this work, is to design interactive proofs for computation that has access to an oracle, to one of these black box functions. And these are also called relativizing interactive proofs. And we even have this quote from the UK AI Safety Institute team, and they say that in order to be relevant for AI safety purposes, an interactive proof result has to relativize. So I think, also point out that beyond just representing human judgment, an arbitrary oracle could represent any function, right? So if we had these interactive proofs that worked for computation with access to any arbitrary oracle, this would give us a lot of expressive power, and I think this is their point. So because we don't know what sorts of AI capabilities might emerge in the future, it's important to have these interactive proofs for as general a computation as possible. And then, as you probably guessed, these standard interactive proof results don't relativize. So maybe one of the most fundamental results in interactive proofs is IP equals p-space due to Shamir in 1989, and it's well known that this result doesn't relativize, or at least the p-space containing IP direction doesn't relativize. And so in a recent work by Irving, Cristiano, and Amode, they pointed out that if we want to recover relativization, what we could do is replace the single prover in an interactive proof with two debating provers. So debate is like in this schematic here, we have two provers who are going to debate each other, and a verifier who doesn't participate in the debate himself, but he's able to see what's going on. At the end, he makes some decision. So in more detail, it's a protocol between two powerful provers who hold opposing claims and a weak verifier, where the provers are going to engage in this interactive protocol, aka a debate, with each other to try to convince the verifier that their claim is valid. And at the end, the verifier sees their transcript and decides who wins. So this definition, again, is due to Irving, Cristiano, and Amode in 2018. And in this work, they also consider using debate for real-world applications. So they do this experiment where they have a debate between two provers, Alice and Bob, who each claim that this image containing an integer contains a different integer. So Alice claims that it contains 6, and Bob claims that it contains 5. And the judge is not able to see this image. So in alternating rounds, Alice is going to reveal a pixel of the image, and Bob is going to reveal a pixel. And at the end, the judge sees all the pixels that were revealed and guesses what the integer in the image actually was. So they show that, or they found out that in this experiment, the honest prover actually wins the majority of the time.
What algorithms did they use for the provers here?
Yeah, I guess the provers are like 2 AI models.
Okay, cool. Cool experiment.
Yeah, so, okay, and then they show that, this debate equals p-space, or rather, okay, so they show that debate is equal to p-space and that this result relativizes. So yeah, it seems like, that debate is really appropriate for this scalable oversight setting. But debate also has its limitations, right? So in particular, in order to use debate for scalable oversight, we need to make these assumptions which might or might not be realistic. So we first assume that the AI models are properly incentivized to debate. And secondly, that the AIs, they're kind of symmetric, they have the same computational abilities. And finally, I think the most worrying assumption out of these is that we have to assume one of the AIs is actually telling the truth. So this assumption hinges on this claim that it's harder to lie than to repeat a lie. So what's going on is that the AI models are incentivized to win the debate game. At the end of the game, the verifier makes a decision as to who wins. So they're only going to want to tell the truth if it's harder to win by lying than it is by winning by telling the truth. Yeah.
How powerful are provers you're thinking about? Like how powerful are you modeling the AI to be?
Yeah, so we're going to be considering like this doubly-efficient model where the provers are also polynomial time. So then this was the question that we were considering in this work. So can we construct a single prover interactive proof that relativizes? And so before talking more about this question, I'll mention some more things about our model, which is this one of doubly-efficient interactive proofs. So in this model, the honest prover is going to run in polynomial time, and the verifier is even more efficient running in, say, near linear time. The verifier is going to make very few queries to the oracle. So we're going to be modeling the underlying computation as a circuit. So we're going to require that the verifier makes a sublinear number of queries in the number of oracle gates in this circuit. So in particular, this means that the verifier is not able to make all the queries that he would need in order to perform this computation by himself. I'll say that the first bullet, right, captures like the scalable oversight setting where we're always taking the prover to be an AI model. So even though AI models are powerful, they're still polynomial time algorithms. The second bullet captures the restriction that we want, that where the protocol is very efficient in terms of calls to the oracle, like in terms of calls to human judgment. And so the third point I wanted to make is that even though we require the honest provers to run in polynomial time in a doubly efficient interactive proof, soundness in a proof system is still going to hold even against these computationally unbounded provers. So we still have this stronger soundness condition. I will say that, I think argument systems where soundness holds against only the computationally bounded provers also probably suffices for this AI safety setting. So this definition was inspired by doubly efficient interactive proofs, which were introduced by Goldwasser, Fry, and Rothblum in 2013, and also by doubly efficient debate, which is this doubly efficient analog of debate where both the provers run in polynomial time, that was introduced by Brown Cohen, Irving, and Piliaris in 2023. Okay. So again, the question was, can we construct a single prover interactive proof that relativizes? And we want to do it in this doubly efficient model. And the answer is no, at least not for arbitrary computations. So this was observed by Barbara, Chiesa, and Guan in 2020. change the answer to just one oracle gate, suddenly the entire the output of the entire computation changes. If this is the case, then if we require that the verifier can't make all the queries that he would need in order to perform this computation by himself, then we just can't have an interactive proof because the prover could lie on just this query that the verifier doesn't make, and then change the output of the computation, and we wouldn't be able to catch it. So for these very unstable sorts of computations, we can't do anything.
Actually, I don't think they were motivated by AI safety when they like proved this. Like, do you remember what was like the context of the paper? I forget.
Yeah, I think they were considering like this random oracle model, like relativized sixteenths arguments in this random oracle model.
Okay.
Yeah, okay, so then this work is going to consider doubly efficient single prover relativizing interactive proof and argument systems for these two natural restricted settings.
Sorry, so on this slide and the previous slide, now like this slide is saying the oracle is a low degree polynomial, the previous slide is saying that the oracle has gates. I thought you were modeling the oracle as a black box.
Yeah, so what I mean actually is like the underlying computation that the prover and verifier are engaging. So the prover is going to make a claim that like some algorithm input x, outputs 1, and we're going to be modeling the algorithm as some circuit that has oracle gates. Yeah, so we're going to be considering these doubly-efficient interactive proof and argument systems in these two restricted but still, I think, natural settings. So the first one is where the computation is stable, so it's robust, in the sense that the output doesn't change, even if at most a small fraction of the oracle answers are incorrect. And the second is where the oracle is some low degree polynomial. So yeah, I think in particular, in this first setting seems relevant for applications because if you were, for instance, going to take your oracle to represent human judgment, which is already some kind of shaky notion, I think you would probably want your computation to not just flip because like the answer to a few of the oracle calls are changed. Yeah, so in this talk, I'll be covering this first setting. Yeah, so now I'll say a bit more about the model of computation that we consider. So we're going to be considering oracle circuits, which are just Boolean circuits that have access to an oracle. Yeah, so they also contain oracle gates along with the usual gates. So a more fuller definition is that it's a diagram that shows how to obtain an output bit from a binary input string by applying some sequence of OR and not operations and also calls to this oracle. And a layered oracle circuit is going to be one where we assume it takes the form, the oracle queries are partitioned into D layers, so we have D layers of oracle gates. In this drawing, this circuit has 2 layers of oracle gates. And an oracle circuit will say that it makes adaptive queries to the oracle if the queries are allowed to depend on answers to previous oracle queries. So this, you can also think of this as an oracle circuit that might contain multiple layers of these oracle gates. Yeah, and this is a more formal definition of robustness. So we're going to define epsilon robustness like this. Let's let C be an oracle circuit and let X be an input to C. Then this computation C of X is going to involve some sequence of queries and answers to this oracle, which we could denote by this string Q sub X. And we're going to call another string of this form with queries and answers Q sub X prime valid if every query Q prime in this string is computed correctly from X and the previous answers A prime. So we're going to say then that the circuit C is epsilon robust if for every input X, for every valid q sub x prime that can be obtained from q sub x by changing at most an epsilon fraction of positions in q sub x. The computation c of x, where we kind of substitute q sub x prime in for q sub x, is going to produce the same output. Yeah, so this is trying to capture this notion that even if we change at most a epsilon fraction of the answers to Oracle queries in this computation, the output still remains the same. Okay, so now as a warm-up, yeah, let's consider an interactive proof for this robust setting where we assume that the circuit must make non-adaptive queries to the Oracle. So another way of saying this is that the circuit only has one layer of Oracle gates, like in this drawing here. So our theorem in this setting is, let's let L be a language that has epsilon robust Oracle circuits making non-adaptive Oracle queries with L Oracle gates depth D and size S. Then there's a doubly efficient interactive proof system for L that has the following parameters. So the first is that the prover runs in time poly in the size of the circuit. The verifier runs in this amount of time, and he makes order 1 over epsilon Oracle queries. And this is going to be a variable communication. So in order to prove this result, we're going to need to make use of some tools from this theory, this literature on interactive proofs. So the first tool that we're going to need is called an interactive proof of proximity, or an IPP. So this is some sort of doubly efficient interactive proof where the verifier is extremely efficient. So he runs in sublinear time in the length of the input. And he, yeah, that means that he can't read the entire input, and we assume that in this model he can query any bit of the input so that the input is kind of treated as an oracle. And this interactive proof of proximity is going to satisfy the usual definition of completeness. And also, because we can't get the regular notion of soundness, always it's going to satisfy this relaxed notion of soundness. So if the input differs in at least an epsilon fraction of bits from every input q prime in the language, then the verifier should reject with probability, say, at least 2/3. So this is saying, right, if the input is far from the language, the verifier should reject. We don't make any claims as to what happens if the input is close to something in the language. And this definition is due to Rothblum and Dickerson in 2013. Okay, and the IPP with the best known parameters is due to Rothblum in 2020. So they present IPP that achieves these parameters. And I think the important note to take from this slide is that in their IPP construction, the verifier is able to make all queries to the input at the end of the interaction. So we're going to use this crucially in our protocols. Yeah, and then finally, we'll also be needing a doubly efficient interactive proof. So we're going to need this construction due to Goldwasser, Kalai, and Rothblum in 2013. And so they present a doubly efficient interactive proof for low space computation. Okay, so going back to this IP for this non-adaptive setting, the setup is going to be like this. We have a prover and a verifier, and they're given input X, and this epsilon robust Oracle circuit C that makes non-adaptive Oracle queries, and access to the Oracle. And now the prover is going to claim that C of X is equal to 1, and P and B are going to engage in some interactive proof to prove this. So, yeah.
Does the verifier doesn't get the circuit though, right?
Yeah, he has access to like a succinct description of the circuit.
But then why can't he just write it himself and then check?
Yeah, he's like not able to, I guess he's too efficient to be able to run it himself, but he can.
Oh. Oh, the description is of the circuit is like too succinct?
Yeah, or like he has access to this succinct description. Maybe he can like access any gate in the circuit, but he can't run the computation time.
Oh, because there's too many queries or something?
Yeah, he's just too
I think I think also like a lot of constructions allow you to like take this circuit once and do like linear work with respect to the circuit once, and then like you can run this protocol with respect to like a lot of inputs. So you can do this also for general circuits. Yeah, I don't know what particularly use, but often do that. Oops.
Okay, yeah, so maybe the initial idea for this protocol is just to do an IPP. So the idea is to do an IPP maybe on this string of queries Q. So we're going to have P and VIPP do an epsilon IPP on input XQ to show that this output bit 1 is computed correctly from X and the answers to these Oracle queries. And at the end of this IPP, the IPP verifier is going to need to query some indices in this string Q. So he'll handle this by asking P, and then finally we'll just have the accept exactly when this IPP verifier accepts. So yeah, so I'll note that this differs from a standard IPP in that in a standard IPP, like the input is written in the sky, it's reliable, but here the input lies with the prover. The verifier VIPP needs to ask the prover for positions in it, and of course the prover must lie. So yeah, this isn't a secure protocol as it stands. So as a fix, we're just going to do something really straightforward. We're going to have you check that what he sent is actually correct. So I guess one really straightforward way of doing this would just be to have V compute this Q at positions J himself. But to achieve like better parameters, we're going to have V engage in a doubly efficient interactive proof of the prover in order to prove this. Yeah, so this is the protocol then. So what's going to happen now is at the end of this IPP, the IPP sends the indices he wants to query J to P, and P sends this Q prime string, which is supposed to be Q at these indices. And now P and the DIP verifier are going to do a DIP to show that the queries in this string are actually like the queries in Q at the indices in J. And also we'll have you check that the Oracle calls are correct. And if all these checks pass and the verifiers accept, then we'll have the accept, and otherwise they'll reject. Yeah, so soundness, the argument goes like this. So let's suppose that the accepts, and we want to show that with high probability, the output of the circuit is indeed 1. So by soundness of this doubly efficient interactive proof, we have that with high probability, Q prime is actually going to be equal to Q at these indices in J. And so then if this is the case, from the view of the IPP verifier, this IPP is just going to look the same as a standard IPP. So we can invoke soundness. By soundness of the IPP with high probability, then Q is epsilon close to a string Q double prime that satisfies this condition in step 1, that 1 is computed correctly from X and these answers to Oracle queries. And then since C is epsilon robust, we'll also have that C of X is equal to 1. Okay, so now let's move on to this more general adaptive setting. So now we're going to be looking at interactive proofs for this bounded depth adaptive setting. Bounded depth adaptive means so we'll say that like D bounded depth adaptive means that the Oracle circuit is allowed to contain D layers of Oracle gates. And so our theorem in this setting is that for any constant E, if we let L be a language that has epsilon robust Oracle circuits, or epsilon equal to the order L to the negative 1 over 2D, with D layers of Oracle weights, L Oracle weights in each layer, depth big D and size big S, then there's going to be a doubly efficient interactive proof system for L with the following parameters. So the prover again is going to run in time polynomial in S. The verifier will run in this amount of time and make order L to the 1 minus 1 over 2D Oracle queries, and this is going to be their total communication. So in this drawing, we have this two bounded depth adaptive oracle circuits. So an oracle circuit with two layers of oracle gates, and we'll use Q1 to represent the string of queries and answers corresponding to this first layer of oracle gates, and Q2 to represent the string corresponding to the second layer. Alright, so here's our setup. The prover and the verifier are both given this input and this oracle circuit and access to this oracle, and he is going to claim that the output of C input X is 1. Okay, so for a protocol, the idea is maybe we can just start like we did before. So we're just going to start with an IPP. Like before, we'll have P and an IPP verifier to epsilon over 2 IPP on this input X Q2 to show that 1 is computed correctly from X and the answers to oracle gates in the second layer. So at the end, the IPP verifier will need to query some indices J2 of Q2, and we'll have P send this Q2 prime. So at this point, we can't continue like before because now it might no longer be efficient for us to verify that Q2 prime is correct because the queries to the second layer of oracle gates can depend on any number of queries from or any number of answers from the first layer. So we can't just continue exactly as before, but the idea is, okay, maybe we just do another IPP. So now we're going to have P and a second IPP verifier do this epsilon over 2 IPP on this input to show that the queries that this first IPP verifier wanted to make are computed correctly from X and the answers to the first layer of oracle gates. So at the end, the second IPP verifier is going to send the indices J1 that he wants to query to P, and P will send Q1 prime. And now maybe we'll just continue like before. So we'll do this VIP and check that all the oracle calls are correct and accept if and only if everybody accepts and all the cases. Okay. But there is a problem with this protocol, which is that P here can actually adaptively choose the queries, the answers to the queries Q2 prime after seeing the queries that J2, that the IPP verifier wants to make. So this means that the input to this IPP is actually not fixed before the start of the IPP. P can change what the input is after the start. So this isn't an IPP. And yeah, so what we would really like to do is to kind of have P commit to the input before the start of the IPP. And so the idea to fix this problem is we're going to ask, like, how many Q2 primes are there actually such that V would accept? So in order for V to accept, notice that Q2 prime has to be correctly computed from some string that's epsilon over 2 close to Q1. So this gives us at most sum from I equals 0 to epsilon L over 2 of L choose I possibilities. This is about L to the epsilon L over 2 because we can pick I positions out of the L positions in Q1 to change for any I from 0 to epsilon L over 2. Okay, so now the idea is since we only have this many possibilities, we're just going to bind P to a particular one using a universal hash before the start of protocol. So before the start of the IPP. Okay, so now I'll introduce what a universal hash family is. So it's going to be a randomized algorithm that has the following guarantee. So for all distinct elements X and Y in the universe, the probability over the choice of the random key from this key space K, that H of Kx is equal to H of Ky is at most 1 over the size of M. So there's a well-known efficient construction of a universal hash family. And for us, we're going to want the strings in M to be of length about log of this L to the epsilon L over 2, so that for any particular hash, with good probability, there's at most one of these valid choices for Q2 prime that hash to that hash. So now before the IDPs, we'll have P hash these blocks of Q2 and send them to the verifier, which is going to bind P. Okay, so this is the final protocol. We'll have V sample this random key K and send the key to the prover. And now P is going to chop up Q2 into some contiguous blocks and hash these blocks using the key and send the hashes to V, which effectively commits the prover to the input. And now, after this first IDP, when the verifier wants to make the queries, he's also going to ask P to send the corresponding blocks. And now we're going to check that the blocks actually hash to the hashes that P committed to at the start, and reject if this isn't the case, and then the rest of the protocol will just follow like before.
This is a bit of a naive question. What is stopping the prover from, like the guarantee of the universal hash function is like over the randomness of the key, right? But the verifier immediately sends the key to the prover, so what's stopping the prover for looking for like hash collisions basically? That it's inefficient.
Oh, sorry, can you say more what you mean by?
Like, I don't, like, the guarantee is that it's uniform in like over the distribution of the keys, but there's no probability here, right? Like, the verifier, like, no matter how the verifier chooses a key, from the perspective of the prover, I mean, they just get it, right?
Yeah, I guess.
I mean, another way to ask this is like, why don't you need a collision-resistant hash function, like with computational assumptions? Like that's usually you need like Merkle trees or something if you use interactive system protocols.
Yeah, so maybe I'm not understanding the question very well, but like this universal hash family that we use has like this statistical soundness guarantee, so yeah.
So I think the question is, K is already known to the prover, so then maliciously choose Q2 to engineer these collisions.
So I think usually when you're doing like Merkle trees, you're mapping some large thing to a small hash.
Yeah.
Here, our hash is actually got
Same size.
more bits than the universe size of the thing we're hashing.
I see.
And so there actually are no pairs that collide.
I see.
Like the most likely event, there's some probability involved here, but most likely there's no pairs that collide. So there's
Okay.
no attack. Is that reasonable?
Okay, I think so.
But if the hash is larger than a universe size, why are you using hashes at all?
Yeah, what
Because
is
the
the-
universe is unknown to us a priori. It's
Okay.
these
Fair.
the some number of things that are close to it. Yeah.
Okay.
Aren't they like inputs of the oracles, like the universe size? Like, aren't we saying that?
The universe size is the number of things that a few slides ago we counted the number of Q2 primes that are closest to Q1, right? Right.
Yeah, so we want to say that unless one of these P2 primes hashes to the hash that we sent in step one.
So I am kind of confused why. So we're sending this hash to bind ourselves to the Q2 prime that we're going to send, right?
Yeah.
Why not just send Q2 prime to bind ourselves to the Q2 prime that we're going to send?
Because I guess we don't want to. I think so. We don't want to do this like before we know the queries to the what the IDP verifier is going to make to this this IDP. So. with high probability, we have that Q1 prime is equal to Q1 at these indices in J1. So from this view of the second IPP verifier, the second IPP is just going to look the same as a standard IPP where the input was Q1. And so that means that we can invoke the soundness of this IPP. So, and then by the soundness, there are going to be at most L to the epsilon over 2 choices that are possible for Q2 prime. So then we use the security of this universal hash family. So with high probability, at least one of these choices is going to hash to the hash that this prover sent in step 1. So now from the view of the first IPP verifier, the first IPP is also going to be the same as a standard IPP because the input was fixed before the start. So then, since C is epsilon robust, we have that C of x is equal to 1. Yeah, and then I'll just end on some open questions. So I think one natural question is to ask, like, what other assumptions could we make on either the structure of the circuit or on the oracle that would allow us to obtain these relativizing doubly efficient interactive proofs? Another question might be, like, which circuits can we turn into robust circuits? So can we identify some class of circuits that have an equivalent, not too much larger, robust circuit? And then finally, I think a question that seems really interesting is whether we could construct protocols for a setting where, it's not only that the verifier can't perform this computation by himself, but he doesn't even know, like, what C is supposed to be. So this might capture this problem of scalable oversight. For example, in a setting where it's not only the case that the task is too time consuming for us, it's that we don't even really know how